we are doing section 2.3, which is the product and quotient rules for derivatives and higher order derivatives. So the product rules, when we have two functions, we multiply them together. Each function individually can be derived. To find the product derivative of f times g, we take f of x times g prime of x. That means we take the derivative of g plus g of x times f prime of x. We'll need to learn that, but for now we can reference it if we need to. Keep it right there. So here we have the derivative h of x, where we have two functions multiplied together. The first one's f, second one's g. To find the derivative, we take f times the derivative of g plus g times the derivative of f. So it looks like we're going to have a lot of foiling to do. 12x minus 8x squared plus FOIL 15 minus 20x plus 12x minus 16x squared. And then we'll combine our like terms to simplify. Always simplify. We have 3x terms. Combines to 4x. We also have negative 8x squared and negative 16x squared, which would be negative 24x squared. And only one constant, which is 15. Alright, so here we have the product rule with two different functions. Our first function is 3x squared. Our second function is sine of x. So the product rule is take f, leave it alone, times the derivative of g, which is cosine x, plus g f prime. That's really as simple as I need it. Usually the x terms go in front of the trig function, so if you want to rewrite it as 3x squared cosine x plus 6x sine x, that's probably a better answer. Okay, so here we have to use the product rule for the first term, but not the second term of this equation. So we have f here and g here. Derivative, leave f alone, times the derivative of g, which is negative sine x, plus g times the derivative of f, which is 2. Derivative of 2 sine x is 2 cosine x. Find like terms. These two are actually the opposites of one another, so they cancel. Our answer is just negative 2x sine x. Now we have the quotient rule, which is a little bit more difficult than the product rule was. So we have two differentiable functions, f and g. This time we are dividing. The quotient rule is g of x times f prime of x minus f of x, g prime of x, divided by g of x squared. Now, using the quotient rule, keep that in sight. We are trying to find the derivative of 5x minus 2 over x squared plus 1. Top is f, bottom is g. So if we're taking the quotient rule here, we have to leave g alone, times the derivative of f, which is 5, minus leaving f alone, times the derivative of g, all over g squared. When you have a polynomial on the bottom like that, x squared plus 1 squared, you don't have to multiply that out. You can leave it as x squared plus 1 squared. So simplifying on top, 5x squared plus 5 minus 10x squared plus 4x combine all the like terms, we just have the x squared terms in common. Put it in descending order of power. We can leave our answer like that. Find an equation of the tangent line to the graph of 3 minus 1 over x plus 5 at negative 1, 1. Well, first off, when we rewrite this function, we have a very complex fraction. We need to get rid of that. The way we're going to do that is multiply by x over x. which makes the top 3x minus 1, and the bottom x squared plus 5x. Now we have our f and g, and we can do the quotient rule, which is g. F prime minus f g prime over g squared. So simplifying and multiplying through. Okay, if we look at the top terms and simplify all that we can, turns into negative 6x squared minus 13x plus 5, and then combine all of our like terms, we get negative 3x squared plus 2x plus 5 over x squared plus 5x squared. And then to find out what the derivative, that's the derivative we need of the slope at negative 1, 1. We're going to put negative 1 in. When we do that, we get 0, which makes this a little bit easier. So if we're going through negative 1, 1, y minus 1 equals 0 times x plus 1, or y equals 1 is our line. Okay, now we're going to use the constant multiple rule to change our originals into a little bit simpler of an equation to differentiate. If we divide by 6, it's also the same thing as multiplying by 1/6. Take the derivative, leave the 1/6 out if you'd like, and simplify. And if you looked at that and thought right away that that would be the quotient rule, it could be, but it would just be longer than what we just did. Okay, rewriting this, just 5/8 as the number out front. 5/8 times 4x cubed, which is 5/2 x to the third. Okay, next one, if we pull out that negative 3/7, then we have x's on top and bottom. We can just go ahead and cancel an x right away. So 3 minus 2x is all we have left, as you notice. The x's cancel. So take the derivative of that. Negative 3/7 times negative 2 is 6/7. And the last one, we have to bring that exponent up to the top before we can take the derivative, make it negative. 9/5 times negative 2, x to the negative 3, which is negative 18 over 5x cubed. Okay, so we did sine and cosine, we know the derivatives of those, but we have other trig functions we need to take the derivative of. The derivative of tangent is secant squared x. Cotangent is negative cosecant squared x. Secant is secant tangent, and cosecant is negative cosecant cotangent. So I'll take the derivative of these functions that include trig functions. Prime of a is 1 minus secant squared x. B, we need to do the product rule because we have function f and function g. So y prime f g prime plus g f prime. And you can take a secant out if you want to, but I wouldn't mark it wrong if you didn't. Okay, so we're going to take the derivative of both these forms. First, we're going to start on the left-hand side form. We're going to have to do the quotient rule to find the derivative of this, which is g. Derivative of the top is also sine of x minus f g prime g squared distribute through. Sine squared plus cosine squared is 1. And that would be simple as we would go. Let's try to keep that in sight as we work with the right-hand side. Cosecant minus cotangent. Derivative of cosecant is negative cosecant x cotangent x. And negative cotangent turns into positive cosecant squared. And this should not be squared here. It should just be cosine. So if you actually went through and looked at this, it would be the same answer. This one turns into cosecant squared minus cosine over sine times 1 over sine. Cosine over sine is cotangent, and 1 over sine is cosecant. So these are actually exactly identical. So if you start with a form like 1 minus cosine over sine, it's obviously beneficial to you to simplify it first because your differentiating becomes a lot easier. The last one we're going to talk about is higher order derivatives. That means instead of just taking the derivative once, we can take it several times. If we're dealing with the position function, we found out a couple sections ago that if we take the derivative of the position function, it turns into velocity. If you take the derivative of the velocity function, it turns into acceleration. So we can just take the derivative of position twice to find the acceleration function. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these objects is given by the same function. S of t equals negative 81/100th t squared plus 2, where S of t is the height and t is time in seconds. What is the ratio of Earth's gravitational force to the moon's? So we need to, this is representing the moon, we need to find the acceleration function. So if this is position, we need to find first derivative, which gives us velocity, which is negative 1.62t. And if we take it again, that is the acceleration function, which is negative 1.62. So in general, it's negative 1.62 is a gravitational pull, and we know that Earth's is negative 9.8 meters per second squared. So if we're doing the ratio of Earth to moon, negative 9.8 to negative 1.62, it's approximately 6.05. And that's what this question wanted. So that was the product and quotient rules.